Okay, rather than starting out with problems today, we're going to jump right into new material since there really wasn't a whole lot to do from yesterday, just a lot of vocabulary. So, was there any questions on the homework from yesterday? Okay, so then let's take a peek at some of the vocabulary things that we learned yesterday and how they actually relate to each other. One of them that we've already hinted at is probably the most important one for machining applications is this one. What's that line there called? A tangent. And anytime we have a tangent to a circle, the radius of that circle that comes to that point of tangency, that should be straight, but it's not, is always going to form a right angle. It's going to be perpendicular to that tangent. So this helps us out in a lot of applications. V-blocks. You know that the radius of that circle is going to be perpendicular to that tangent on each side. Now we're going to know that the two radii are going to be equal, so that's going to lead to some other things as well that we can look at. For example, let's say we're going to take this and connect the center of the circle to the intersection of those two tangents. This does a couple very important things. First of all, we know that that line, that blue line we just drew in, is equal to itself, don't we? We know that this side is equal to that side, correct? And we know those are both right angles. You know, radius is equal to itself, and it always forms a perpendicular to tangent. Since that is a right angle there, if we know two sides, we know the third side, don't we? A squared plus b squared equals c squared. So what we have here is we have two triangles that we know that all three sides are the same. So what does that tell us about those two triangles? They're equal. If two triangles have the same three sides, they must be the same triangle. They can be mirror images of each other, but they're still the same triangle. So that leads us then to know that this angle and this angle are the same, and this angle here and this angle here are the same. In fact, that is always true when two tangents to the same circle intersect. The distance from that point of tangency to where they intersect is going to be the same for both tangents because it creates two equal triangles like that. So our radius always hits a tangent at a right angle. The next thing I want to look at is what if we have a chord and a radius hitting the chord. Now obviously a radius does not have to hit that chord at a right angle. It could go like that and hit the chord. That's definitely not a right angle. You know, that's a radius, definitely not a right angle. So what I want to look at is what if the radius does hit that chord at a right angle? What do we know? Well, we will know again that this angle and that angle are both right angles. If we have one right angle at two intersecting lines, we have four right angles, don't we? What do we know about this and this? They're equal. They're both radii of the circle. All the radii of that circle are equal to each other. What do we know about the distance from here to here? Well, it's in both triangles, isn't it? So again, just like we had up here, we had a right triangle where we knew two sides were the same. If we know two sides are the same, then we also know the third side's the same, don't we? Because a squared plus b squared equals c squared. In a right triangle, we only need to know two of the sides. So what that is telling us is if we have that radius that hits that chord at a right angle, it cuts the chord in half. It bisects the chord. Now, going the other direction, would the opposite be true? If I have a chord here, if I draw a radius in that happens to cut that chord in half, does it have to hit that chord at a right angle? Well, common sense would tell us probably yeah, but let's double check it. So those two pieces are equal, the two blue pieces are equal. The green pieces, of course, are radii. One radius is equal to another radius. And of course, this piece is still equal to itself. So we know that we have two triangles, right? That are the same, that have the same three sides. How does that equate to being a right angle? Here. Well, we know that this angle and this angle are equal, don't we? Because the two triangles are equal. And we know this is a straight line. So that means, if I call that angle 1 and angle 2, angle 1 and angle 2 are supplementary. They add to 180 degrees, and they're equal. So if they're equal and supplementary, they must each be 90 degrees, half of the 180. So yes, those are right angles. So that is another condition of a relationship between our radius and our chords. If the radius hits the chord at a right angle, then it cuts the chord in half. And the opposite, if the radius cuts the chord in half, then it also hits it at a right angle. This is one we talked about at the end of last semester a little bit. If I have two chords in a triangle that intersect each other, so let's say that this length here is 4. We're going to call this length 3, this length 12, this length x, unknown. When two chords intersect each other, the product of their pieces is the same for both chords. What do I mean by that? Well, this chord here is cut into two pieces, 3 and 12. The product of their pieces is 3 times 12. This chord here is cut into two pieces, 4 and x. So the product of their pieces would be 4 times x. Those must be the same for the two chords. So 3 times 12 is 36, equals 4x. We divide by 4, x has to be 9. I don't know if you recall back last semester, we did this for arcs. For you guys, what it would equate to would be dealing with shaving a piece off of a round stock. If you know that what you're going to be taking off that round stock is, oh, let's say that ends up being 240 thousandths wide and deep, that this is going to be 60 thousandths deep. You can find the radius of that circle. Remember, we can trace this all the way down. Well, this actually comes into what we just learned up there. If we draw that so that it's perpendicular here, it must cut this in half, right? That's a radius, so it's going through the center. It actually is completing our diameter. That diameter is made up of two radii. So if I call this length here x, what do I know about this length here? It's 120. Where did I get 120 for that? Because it has to cut that in half. The radius going perpendicular to that chord has to cut it in half. So I know that 120 thousandths times 120 thousandths, that's the two pieces of that chord, have to have the same product as the two pieces of the other chord. So that would be 60 thousandths times x. So again, I'm going to multiply these together to get 0.0144. Now I'm going to divide by the 60 thousandths. Which gives us what? 0.240. Does that look right? Yeah, so x is 240 thousandths. So that gives us that we must use a piece of stock that has a diameter of 300 thousandths, or 3/10 of an inch. I said 300 thousandths. I shouldn't say 3/10. It's mixing terminology a bit. 300 thousandths of an inch is the diameter of that piece. Make sense? Okay. So now let's look at the arcs and the angles that are created with those arcs. One thing that we learned at the end of last semester is that central angle is related to the arc length. Remember, that is a central angle there. It's called a central angle because its vertex is at the center. So if that is a 55-degree angle, and I have a radius of 8 millimeters, the arc length is found as a fraction of the circumference of the circle. So the circumference of that whole circle is 2 times pi times 8. 2 times pi times 8 is about 50.24 millimeters. So then that arc length there is found 50.24 millimeters times that central angle, 55 degrees, over, well, the whole circle is 360 degrees. So it's 7.68 millimeters of arc length there. So that's stuff that we've looked at before. What if in this same circle, I have another 55-degree angle? What do I know about that arc length? 7.68 millimeters. In fact, it doesn't even have to be in the same circle. In any circle with a radius of 8 millimeters, a 55-degree central angle is going to give us an arc length of 7.68. Because of that relationship, rather than always calculating that arc length, we'll sometimes name that arc in degrees from the central angle. It's 55 degrees. This is also a 55-degree angle. And what that is, or a 55-degree arc, I should say. What that is telling us is that arc is 55/360th of the whole circle. So I mean, the degrees itself, if you look at that arc, it's not, the degrees don't make much sense to describe a length, but it's just saying that that is that fraction of the full circle. So then later you can be given the radius and find that arc length. That's one of the reasons why they use radians to measure angles. When you're talking about radian angles, it's much quicker to convert between the angle and the arc length. You don't have to use pi when you use radians. What if I create an arc, or sorry, if I create a new central angle here, It's 110 degrees. Yes, that arc length is going to be the 7.68 times 2, or 15.36 millimeters. Why? Because 110 is double 55. Within the same circle, or again, between circles that have the same radius, if I am comparing, I'm just going to call this arc A and this arc B. The ratio of the angles. Now that little M in front says the measure of angle A, is what that's saying, the degrees of angle A. That means degrees of angle B. The ratio of the angle measurements is equal to the ratio of the arc lengths. So if I tell you that this is a 30-degree angle, and that this arc length out here is 12 millimeters. If I come over here and tell you that this is a 75-degree angle, to find this arc length, I have my ratio of angles, 30 degrees to 75 degrees equals 12 millimeters over that missing arc length. I'll cross multiply. 75 times 12 divided by 30 is 30. That arc length is 30 millimeters. Make sense? So this is what we would refer to as a direct relationship. The angle gets bigger, the arc gets bigger. The angle gets smaller, the arc gets smaller. Not all of our arcs can be defined by a central angle like that. Sometimes the vertex of our angle has to be somewhere else. To illustrate this, I am going to look at, this is a central angle of 60 degrees. What I'm going to do is this. I'm going to extend this across to make it a full diameter. Then I'm going to connect this point here over there. First of all, does anybody remember the name for that kind of an angle there with its vertex on the circle? It's called an inscribed angle. Remember, inscribed means vertices on the circle. What we know here, we know this and this are equal because they're radii, right? This is also equal to them because that's a radius. We know this angle is the supplement of that one. It's 120 degrees, right? Well, if that's 120 degrees, we can find the other two because this is an isosceles triangle, which tells us that these angles must be the same, doesn't it? So 180 minus 120 is 60 degrees. So those two angles add up to 60 degrees. They each have to be 30. And if we explore this, no matter what angle we start with here, these angles always end up being half of whatever this one is. So now, I'll try that again. Let's try to extend that concept. Let's say that this angle here is 38 degrees. How would you describe this arc? How many degrees is it? 76 degrees. Very good. Because from this relationship up here, since this inscribed angle is always half of that central angle, if we were to create a central angle here off of this arc, that central angle has to be double the inscribed angle, 76 degrees. So that arc is 76 degrees. So if the inscribed angle, or the central angle is always double the inscribed angle, then the arc is always double the inscribed angle. Or the other way around, the inscribed angle is always half of the arc it intercepts. Pretend that's the center of the circle. If this here is 42 degrees, what is the total of this arc plus that arc? Well, this arc has to be what? 42 degrees, right? This arc here has to be 42 degrees, because this is also 42 degrees. That's the center of the circle. Well, if I move the intersection of those lines, those chords, in this case, they're both diameters. Remember, diameter is just a special chord. If I move that intersection this way, those lines are still parallel to the original ones. You'll see that this arc got smaller, this arc got larger. The question is by how much? Well, because these are parallel here, this piece and this piece are the same. This piece and this piece are the same. So what was gained here is equal to what's lost here. So the total between those two arcs is still 84 degrees. This angle is still 42 degrees, and this angle is still 42 degrees. Pretend that's round. So there's a couple of different ways this can be applied. If I know that this arc here is 18 degrees and this arc here is 34 degrees, I can find these angles. Of course, those two angles are both the same, aren't they? I know that the sum of the two angles, x and x, equals the sum of the two arcs, don't I? So since the angles are the same, one angle is just equal to half the sum of the two arcs. So I add them together and divide by 2. 18 plus 30 is 48. Divide by 2. Oops, 34, thank you. 18 plus 34 is 52. Divided by 2 is 26 degrees. So each of those angles is 26 degrees. The other side of that is if I know that angle is 70 degrees, and I know that this arc here is 28 degrees, I can find this arc. I'm going to call that x, because I know that x plus 28 divided by 2 equals 70 degrees. That the average of those two arcs has to equal this angle. Of course, this is also 70 degrees, right? So now I solve that equation to find my angle, or to find my missing arc. I multiply by 2. 140 equals x plus 28. And then I'll subtract the 28. 112 equals x. So this is a 112 degree arc. So, if I tell you that this arc here is 146 degrees, what's that angle have to be? 73, very good. That's an inscribed angle. Its vertex is on the circle. The inscribed angle is always half the intercepted arc. Well, what if that angle, the vertex is still on the circle, but instead of both sides being chords, one side is a chord and one side is a tangent? Well, and let's say that this arc here, let's give that arc as 108 degrees. Well, let's see what we can figure out from that. There's the center of my circle. What do I know about that angle? The central angle has to equal the arc that intercepts. It's 108 degrees. Well, those are radii. I know they're equal. That tells me that this angle and this angle have to be equal. That's now an isosceles triangle, isn't it? What do I know about those two angles? 180 minus 108 is 72. They add up to 72 degrees. Divided by 2 makes each of them 36, doesn't it? Well, what else do I know on this picture? If this is a tangent, what's this angle? That's 90. That has to be a right angle. Has to make a right angle with my radius. So this is also a right angle. So if that's 36, this is 54 degrees. See the relationship between that angle and the arc? It's the same relationship as this inscribed angle to that arc. It is half of the arc it intercepts. So that vertex is on the circle. That is still an inscribed angle. Even though the one side is not a chord, it's a tangent. Well, what if we have two chords, but they don't intersect inside the circle? Now, first of all, once that chord extends outside of the circle, do you remember what it's called? The angle is an exterior angle. There you go. The line itself, or the line segment itself, becomes a secant because it extends through the circle. From a secant is just a line that has points that are both inside the circle and outside the circle. So that is the secant. Now let's say I tell you that this arc over here is 80 degrees. We'll keep it simple. That tells me a few things. One, pretend that's the center. What does it tell me about that angle? 80 degrees. What would it tell me about this angle? 40 degrees, right? That's an inscribed angle. It'd be half of the 80-degree angle. Now, this exterior angle out here, does it have to be bigger or smaller than 40? It's smaller. The further we get back this way, the smaller that angle gets, isn't it? Well, how do we figure out how much smaller? Well, it depends on this arc here. The bigger that arc is, the further this exterior angle had to be pulled out of the circle, right? So the way we find the size of that exterior angle, or the angle of intersecting secants, it's sometimes called, is we take the major arc, come on, minus the minor arc. if I tell you that this is 24 degrees, which one do you think is the major arc? The big one, the 80. Minus the minor would be the small one, the 24. And just like we did for the intersection of the chords and for inscribed angles, we do divide it by 2. So 80 minus 24 is 56. Divided by 2 is 28 degrees. This angle out here is 28 degrees. Notice that is smaller than the 40. These are two circles that are tangent. Pretend they look like circles. If I connect the centers, those centers, obviously, this is a radius of the little circle. This is the radius of the big circle. I'm just going to use little r and big R. That line connecting the centers is called a line of centers. Not a big necessary vocabulary term. But one thing you need to know is that it must go through that point of tangency. That line of centers is the shortest distance from the center of one circle to the other. The only way it can be the shortest distance is if it goes through that point where the two circles touch. Now, rather than going through the process of proving these, because we're running a little short on time, let's just do this. If I run a line through there, if it is tangent to one circle at that point, that means it is perpendicular to that radius, doesn't it? Well, if it's perpendicular there, what do we know about this angle over here? That must also be a right angle. When two lines intersect, if they form one right angle, they form 4 of them. So it's perpendicular here, which means it must also be tangent to that radius. So when two circles are tangent like that, a line at a point of tangency is perpendicular to both radii. In other words, perpendicular to the line of centers. Now let's put together some of the stuff we have learned here. So let's say that we know this angle over here is 28 degrees. And we know that this arc here is 34 degrees. Can we find that angle there? Why not? How would we find it? Well, to know that angle, if we knew this arc, we know that angle is related to that arc. How? It'll be half of that arc length, right? Half of the degrees of that arc. How could we find this arc here? I'm going to call this arc Y. Call that angle X. Well, we know that Y minus 34. Y is the major arc of these two secants. We know that Y minus 34 divided by 2 has to equal 28 degrees. So we multiply by 2. 56 equals Y minus 34. And then add 34. That is 90 degrees. Y is 90 degrees. This is a 90-degree arc. Which means X then has to be 45 degrees. Now, if that is 45 degrees here, if I tell you that this arc here is a 36-degree arc, and I tell you that that line across there is actually a diameter. That's the center of the circle. I know it's a little off center, but let's say that is a diameter. Can I find this angle here? How? There's a couple of ways I can do it, right? I know this angle has to be, where did I get 18 from? That is an inscribed angle. It's half of the intercepted arc, half of the 36. That's 18. Well, 18 and 45 make 63, so that makes this 117 degrees. Because the three angles of a triangle add up to 180. So that makes this 117 degrees. That wasn't that difficult at all. Now, can I use that information to find this arc? Sure can. I know that's 117, that's 117. I know this is 34. What I really need is this whole arc here. To do that, here, let me do this. I'm going to erase my highlighting there. To do that, what I'm looking at is I have this arc and this arc that are formed by those two intersecting chords, right? So I know that those chords are the average, those angles are the average of those two arcs. So I can find this arc over here because this across here is a diameter. I know that these arcs have to add up to half a circle or 180. So 36 and 34 make 70. This has to be 110 degrees. If that's 110 degrees, that makes this whole arc from here to here 144 degrees. So if I call this up here arc Z around there, I know that Z plus 144 divided by 2 equals 117. Why is this plus here instead of minus like it was up here? This angle was outside the circle. This angle's inside the circle. When the angle's exterior, it's the intersection of secants. It's the difference between the arcs. It's half the difference between the arcs. When it's inside, it's half the sum of the two arcs. So we multiply by 2, and I know we're running low on time. That is 234 equals Z plus 144. We'll subtract 144. That gets to be 90 degrees. Now, because of all the rules that we've seen today, there were probably other ways to go about finding some of the things I did, but I wanted to illustrate certain ones of the concepts that we learned. The toughest part of doing this is looking, because I mean, you can see here, this got pretty cluttered before I was done. And I added the pieces as we went. But you are going to see problems where all these pieces are there to begin with, and you're asked to now find this arc. Well, you're going to have to sort out the pieces that you need for each calculation and which ones you don't, and figure out how to ignore the ones you don't need and only see the ones you do need and find pieces. And there are going to be some of them where you're going to have to go 3 or 4 steps deep. You know, I could have just asked you right away, what is that arc? And you would have had to say, okay, well, I can find this one or whatever. So be patient with yourself. This is a part, you know, the circles and the pieces of the circle are part of this. But another part of this is learning how to pick apart a problem and ignore the information you don't need. And that's going to be the most difficult part of doing some of these. Okay, so in packets, on page 306, there's 9 through 26 that it talks about some of the pieces of the tangents and the chords and the bisectors and stuff. And then on page 315 in that packet, 1 through 26, is more about these arcs and central angles and stuff like that. Somebody want to check and make sure your packet does go up to page 315. I'm pretty sure it does. But this is a pretty thick one. But okay. Okay, perfect. So I know we're still good for today. Let you guys have the last 9 minutes to get started on